first question: what makes the active membranes active? So let's go directly straightforward in.
Yeah, well, the kind of the essence of what is now active membranes really originated for me in the early 2000s, where we had, in 2004, we had patented and we had started the commercialization process for what became nano H2O. And I thought, okay, so we've made a better membrane, quote unquote, higher permeability. And I started thinking about what's next. And at the time, I thought, why do membranes only use one driving force? Pressure only, or temperature only, or concentration only, or electricity only. What if we combined them, and what if we were able to migrate particles, change interfacial, chemistry, and so forth? And so I wrote a grant to the National Water Research Institute. It was funded 2005. We started working on a form of membrane that was electrically conducting, about 2005, 2006. And then, life happens and funds come from different places, and you start working on wherever the funding is coming from. You work on those problems. And so I kind of put the idea a little bit on a shelf until I could come up with some more money to continue pursuing it. And next thing you know, this fellow who was a student and then a postdoc, David Jasby, started working on membranes that could conduct electricity by assembling carbon nanotubes, which is, at the time it was a big thing back in the early 2000s, 2010 timeframe. And they were seeing things that were like everything that I had envisioned in my mind of being able to fend off, particles from sticking to membranes and extreme conditions and alter interfacial chemistry and change solute, rejections. And so really taking a membrane that goes from being a passive physical separation barrier, right, to something which is now more actively participating in the transport of water and solutes through it. It's actively either pushing away or pulling towards it the things that it wants to be at the interface, and pushing away the things that it doesn't want to be, sticking to the membrane and at the interface. And now over the course of time, Jasper and I began collaborating when he came to UCLA in 2017-18 timeframe. And so then it was a combination of, his ideas and my ideas, and it really began to kind of accelerate. And we got to a point a few years ago, we started talking with Aryan, where we're like, we can't write another paper on this. This either has to become a real technology or we have to move on, right? It's like we've beaten it to death. We've done everything you could possibly do. And every time we tried to do something with it, it worked. It is all in the laboratory, right? We did some pilot tests, but they're small scale, pieces of membrane, and had not yet fully contemplated how do you turn a small flat sheet membrane in a plate and frame, filtration, module into something like a spiral wound element, which is a much more complex geometry, much more surface area, and with very specific dimensions and end cap designs and so forth to be compatible with industry standards. We were just playing with little sheets of paper, right? But I think Aryan took a look at what we had done and what we were doing, and you kind of see that light bulb go off in somebody when their eyes light up and they smile and he goes, yeah, I think I can do something with that. And so that was sort of the process of kind of through the course of history and right up until we introduced this conceptually to Aryan. So that's my whole thing was, membranes shouldn't just be passive barriers, right? They can play a more active role in the separation process, in the process of fouling and scaling, and take the technology and really take it to another level.
But can you describe what happens exactly on the membrane surface that is less fouling and scaling tendency?
Yeah, so there's sort of different things in different scenarios. So let's take mineral scaling, which is a big problem in a lot of applications. The amount of water that we can get through the membrane, we call water recovery, is limited by the concentration of minerals on the feed side of the membrane. As you take water out along the length of a system, the mineral concentration goes higher and higher and higher. Eventually, something exceeds its solubility limit and it's going to precipitate. And in general, when minerals are supersaturated, they will begin to precipitate first on a surface before they start forming particles in the bulk. Usually, in the case of membranes, that's really what happens. With there's always some exceptions, but we see the minerals growing straight out of the surface of the membrane a lot of times, and so with the ability to conduct electricity at the interface of the membrane, we can apply different voltages and different waveforms and things like that. And what we found in the laboratory, and I think what we're seeing in the modules and the technology that Arjen and his team have developed, is that we can encourage minerals between two surfaces instead of beginning to form that precipitate or the crystal on the surface. They form it in the bulk in between two surfaces. And so in the context of a membrane, reverse osmosis membrane, for example, in brackish groundwater or something like that, right at the end of the system where normally the minerals start to grow on the surface of the membrane, then they block the membrane, and where the crystal grows, you can't get any water through, right? Well, with active membranes, that electrical field, the way it's applied, it kind of encourages the minerals to precipitate in a bulk, and they just kind of flush out the back end of the system. So I think that's one of the most novel and enabling applications of this technology, because there's no other way to deal with mineral scaling except to throw a bunch of chemicals in the mix, which adds cost, creates, makes the brine now not just salt, but now it's got the chemicals in it. So now you have to dispose of it as an industrial waste. And we the active membranes, they can do that without the chemicals, and they can go to higher water recoveries, because even though you're supersaturated, the minerals are just making particles that flush out the end of the system. And we've seen it over and over in the different projects that Arjen and the team have run. There's other fouling resistance. There's enhanced rejection of certain salts and minerals, and things like boron. We can get higher rejection because we can alter the interfacial pH. And so there's lots of other applications, but I'll just focus on the mineral scaling, because I think that's it's really the most unique, and it's really, to me, because we studied it at UCLA and we know specifically the mechanism, we know what it entails and how to do it, at least in that lab scale, that we understand the mechanisms, and that to me is pretty cool. It's not just, hey, we tried something and it worked. No, we've really studied this thing. We understand the physics. We understand the time scales, the length scales at the submicron, length scales, for example, in milliseconds. And so to me, it's pretty cool technology.
And what is the effect on the fouling side?
So there are different ways of operating, but under certain conditions, with the electrical fields applied, the membrane surface charge is enhanced, like an electrode, if you will, and it becomes highly negatively charged. And so most fouling materials in water, bacteria cells, clay particles, natural organic matter, what have you, or colloidal materials, they all tend to be negatively charged on their surfaces. And so when you have a negatively charged membrane, very highly negatively charged, and a negatively charged particle, there's a natural repulsion, electrostatic repulsion. And that's the main mechanism, just keeping stuff from actually touching the membrane. right? If it's negatively charged, it's going to be repelled away. It's going to stay kind of in the middle of the channel. And in the module construction, you have two membrane surfaces facing each other. And now they're both negatively charged. So particles are just kind of staying right in the middle. And again, they kind of just flush out the system.
That's good. That's good.
What if I may
Yeah, go.
interject? It's very funny because with most of these pilots that we're doing, it's almost an instant effect. When you turn that electricity on, you will immediately see the impact when you monitor the performance of the membrane. In a recent pilot, for the sake of argument, one of our manufacturers made a mistake and build a membrane that wasn't effectively charged, and we were seeing like we don't see the effect that we normally see. And when we took out the membrane and we examined it, we realized that it wasn't simply getting the electricity that it needed to get, and hence it was working just like any other membrane. But the moment you turn on that electricity, you start seeing divergence between the curves. It's an instant phenomenon. And then another beauty of it is that what we're learning is that with that negative charge, if you manipulate it, maybe 20% of the time, 30% of the time, 40% of the time, depending on the water quality that you have, you'll get different effects. In terms of anti-scaling and anti-fouling. Sorry, go ahead.
And can you apply this negative charge to any kind of membrane?
No, has to be electric conducting.
Most like polymeric materials and ceramic materials bear some form of surface charge, but the amount of surface charge is physically limited by the size of the charge functional group. Yeah. Right? So you can't have more than so many charge groups per unit area. And with the active membrane, we're able to control the charge by the application of an electrical field. So we can turn the charge up or down. We can turn it positive or negative. We have much more flexibility. And it's, again, sort of the active nature of the membrane is that it's not just you make it, it's fixed, it stays there, it's passive, it just does what it does. But it's just, it's just like a sieve in the kitchen, right? If things are smaller, they go through, and if they're bigger, they stay in the sieve. This thing is much more active. It's got it's almost like a biological membrane in how it has multiple functionality, multiple driving forces, and it's able to do things. In this scenario, you can tweak the electrical fields and the way that they're applied to fend off mineral scaling. In another scenario, you can do it to fend off fouling. You can make the interface inhospitable for bacteria by elevating the pH, right? So there's all kinds of, and control solute transport, like deprotonate boric acid into borate, and then you get higher rejection, right? And that's another application in seawater, I think, that Active is pursuing. So it just takes one membrane material and allows it to do so many different, to perform so many different functions. I like the name is sort of really describes the nature of the technology. It is actively changing, in real time or application by application, site by site, as needed to accommodate the water quality and the performance expectations. From the early vision through, what I did in the early 2000s, what David Jasby did later on, and then when we came together at UCLA, what we've done together, we still only had a vision, and we had sort of proof of concept at a lab scale. And now to see what Arian and the team have done, taking it out of the lab, taking it into the real world, making it a manufactured product, and applying it into real world desalination and water treatment applications. This is one of the greatest things that you can experience as an inventor, is to see your idea come to life. That's very satisfying.